Okay, so thank you everyone for attending this presentation today. So this presentation will be given by Professor Leopoldo Franquelo. So this he's a distinguished lecturer now from the Industrial Electronic Society, and as you know, we have in New South Wales in Australia the joint chapter with Industrial Application, Industrial Electronic Society, and Power Electronic Society. And Dylan is the chair of the society and vice chair, and then also we have Hansen with us, who is the secretary for the chapter. So I have the honor to present Professor Franquelo, who I have visited, I think, 3 times already in Seville. So Professor Franquelo right now he's a life fellow from the IEEE Society. He's full professor in Seville University, and he has been past editor of the Industrial Electronic Industrial Electronic Transactions, right? And then currently he's the editor-in-chief of the IEEE Open Journal of the Industrial Electronic Society. And he has held so many positions that in the IEEE, especially in the Industrial Electronic Society, so you can have a look to his biography. And he's going to present the work entitled Remaining Useful Lifetime Management of Modular Power Converters, Advantages and Collateral Negative Effects. So Professor Franquelo, please, you can start now.
Thank you. Thank you very much, Ricardo, Dylan, for the presentation, and also for the introduction, sorry, for the invitation to this distinguished lecture. The distinguished lecture has been authorized by the Society, for the Industrial Electronic Society. We will focus on the remaining useful lifetime in power converters, in modular power converters. We will see the advantage and negative effect. We will try to convince you to work on it, okay? Then let me start with this. I will try to make room here. Okay, one important remark before we start is that this is a work done by an international team where other people are joining us, and maybe you can, some of you are interested, and we can talk later about the possibility of cooperating. In the groups that have been doing this work are, of course, my group in Sevilla University, Nacho and Sergio, that are now connected. Also, Professor Marco Liserre in Germany, Gianpaolo Butici in China, in the University of Nottingham, and Vito Giuseppe Monopoli in Bari, in Italy. Each of the group has been contributing with his own expertise, and this have made a multidisciplinary group that I think that have prepared an interesting work that I hope that it is interesting for you. Okay. Also, I want to explain that working with the remaining useful lifetime is a complex matter that needs experts from several matters. For instance, we need to work with the power device aging physics to know how are the phenomena that affect the lifetime of a converter, or a device, a capacitor, whatever. We need people expert in active thermal control method in order to extend the lifetime, but taking into account also the disadvantage that can be corrected with other techniques. Of course, you need to have an expertise in power electronics, especially in modular power converter, because we are working with modular power converters. And of course, you need to know perfectly the harmonic that are produced, because we are changing the conditions, and we need method to compensate the new harmonic. Let's say that we can go to the order. We will start as usual with an introduction explaining most of the phenomenon that things that we will need to explain the concepts. Second, we will go to explain the thermal behavior of the power electronic components, selecting the silicon devices and capacitors. We will explain very briefly several ideas that we need for the modular converters. And later we will explain two examples, one for the inverters or DC to AC converter, and another by applying the method to the DC to DC converters. Finally, we will draw some conclusions, and we will present some bibliographical items that can be useful to us. Then let me go to the thermal behavior of the power electronic converter, and what is the main cause of the failure in the power converter is related to the thermal stress of the power devices. Which kind of failure? Well, you have here one example that that is called a bond wire lift-off, where we are losing, there is a cable and the silicon, and due to the stress, basically the repetition of thermal cycles cause expansion and contraction of the materials. So we lost this soldering. Consequently, this cable is useless, but others in parallel can continue working or not. It depends. It's like here. Also, there are many other causes, but these are the most common. And this one, that is the soldering crack. We have a material here, like copper or alloy, and the silicon, due to the different temperature coefficients, there is an expansion, contraction many times per second. So we will see a crack like this, so there is no possibility to flow the current here, so you reduce this. Then we know that the power semiconductor aging will depend on the average junction temperature, the number of thermal cycles, and their deepness. Let me explain what is this with this example. Imagine an electric car like this, where we have in the time, these are minutes, the accelerator is pushed or is charging, discharging, depending on the condition. We have this profile of the current flowing by one semiconductor, because the driver is pushing the accelerator, the brake, or whatever. Then this will cause a different temperature in the semiconductor, like this. So we have a profile of temperature that will be something like this. In this point, that the current is very high, then we have a very high temperature, and a point like this is low, because we are not demanding a big current, but there is an inertia, of course, and a middle point. So what is the main temperature? It should be something like this. So the number of thermal cycles, this is one thermal cycle, and this is the deepness of one cycle. So we can define this. Of course, we cannot do easily in the industry, in a practical application. We cannot have the semiconductor open and use a camera or sensor to measure the temperature like we are doing here. So in a practical application, we will need to estimate the temperature. How can we do? We can measure easily the temperature in the case, like here, and knowing this temperature with the losses in the semiconductor that can be solved or calculated solving the circuit, then we can multiply or apply the convolution of the complex thermal temperature. So we will have a good estimation of the temperature in the junction. That is the important one. For this, which model we can use? There are two models, Cower and Foster, or any of them, depending on the manufacturer, we may have the information of one or another. Okay, so knowing the losses, the temperature in the case, and the characteristic of the semiconductor, then we can estimate the temperature in the junction. Then we can use one curve like this that is parameterized by for different temperature. In this case, 125 till 77, like this one. Then this is the increase, like this, the increase in the temperature, the deepness of the cycle, and the curve will give us the number of cycles that we have till failure. If we don't have this curve from the manufacturer, we may use one of these two models that are used and defined in this reference, the Coffin-Manson model and the Norris-Land. In both of them give us the number of cycles till failure. Okay, so we can have an estimation of how long it will survive depending on the conditions. Then the full diagram of the estimation of the remaining useful lifetime will start with the emission profile. As we saw before, we can estimate, we can estimate the junction temperature and have a profile of the temperature like this one. Using a rainflow counting algorithm, we will count how many cycles and how deep they are. Using one of the models or the curve, we can estimate the number of cycles still till the failure, and knowing the number of accumulated failure, we can calculate the accumulated damage and calculate the life expectancy. That is what we are looking for. For the power capacitor, that was for the previous slide were for semiconductors. For the power capacitor, we can do something very similar. What are the capacitor technology more adequate? Depends on the application. We have a big variety of manufacturers and technologies that will give us different factors, like the voltage rating, the capacitance, so on, so on, so. But I mark here what is more important for our purpose, that is the equivalent series resistance, or ESR. The ESR is important because all the current flowing to the capacitor is flowing here. So this multiplied by RMS squared will give us the losses. With the losses in the capacitor, we will know the temperature, we can estimate the temperature. So, see if we are in the temperature range and so on. So this ESR it may be very constant depending on the technology, or may change with the harmonics. So the problem will be a little bit more complex. Let's go then. Then in this reference, you can find this model that is normally used for estimating the lifetime. Is different. So this is the time, the expected capacitor lifetime in months or years, taking into account all these values. So the expected in nominal conditions, the voltage and the voltage in nominal, the temperature and the temperature in the rated temperature. So we have to avoid that a capacitor goes like this, but we have to take into account that we are limiting to electrical and thermal stresses, not humidity, mechanical or others. That may be another cause. Then from now, I will mark in the slide in blue, like this, color blue, some something that comes from the previous slide like this, okay? So you can follow easily. Then how we can know this temperature? Then we can do something very similar to estimate the temperature, taking into account the losses, the thermal resistance that should be a date from the manufacturer, and the ambient temperature. So we can see the increase in temperature, and we can calculate the power using the current. But as the ESR may depend on the harmonic, then we have to do the summation of all of them. The total power produced by each of the harmonic in the current flowing by the capacitor. So we need to know the current by the capacitor. Let's introduce a couple of comments on modular converters, some basic concept and pros and cons. Basically, a modular converter will be made with what we call power electronic building block, like this one, that may be more or less complex, but normally very simple ones. Then a modular will need, or we will do the modular in order to have more voltage, more current, more power. So if we use the parallel connection, then we will have a larger current. If we use the series connection, we will have a larger voltage. And if we use a mix of them, we will increase the power, increasing at the same time current and voltage. Okay. In any case, we are increasing the power, of course. So some example just to mention a few of them. For instance, the series connection, we may have what is called the MMC, or modular multi-level converter. In this case, it's an application for high voltage DC transmission, where we have two converters, each of them connecting different grids, and we use a long cable to connect both what is called the transmission in high voltage in DC. This converter, we will come back to this later, but just keep it in your memory. Okay, another option may be a cascade H bridge for a motor drive like this, where we have the grid, the active front end or passive front end in this case, and several connections in series of simple modules. Sorry. In this case, we can see the parallel connection that we have, in this case, three DC-DC converters zooming the current. So it's a parallel connection feeding this capacitor. Or in this case, practically the same, but this is a multi-string, and this is for photovoltaic, and this is a wind energy conversion system. For the mix, we can see the smart transformer as an example, where we have the parallel connection in the input and a series connection in the output. What are the main advantage and disadvantage of the modular converter feature? Basically, we can start by explaining that there is an inherent fault-tolerant capability, because if one module fails, the remaining modules can continue working without the great performance, but working, not totally stopping the system. The output waveform normally have an enhanced quality, so less harmonics, implying that we have a reduced output filter, or especially the cost, size, and volume. Right. We have normally a reduced maintenance cost, because we can make a very fast replacement of the modules, provided that we have spare modules. We can standardize the modules. We may have also a reduction in manufacturing costs because we can use the same PVB firmware for very different applications. A disadvantage, well, there is a higher capital and operation cost, more complex hardware software design, normally, especially the controllers, but this is very well studied and many people are working on it. So we can say that modular converters are today a good option and people knows perfectly how to work with them. A large number of sensor power converters and drivers. Well, it's true, but we have many other advantages and a bigger system size of the non-modular converter. So let's go directly to the thermal management method for modular converter. Imagine that we have a modular converter with n cells. So we have this number of cells. Then the idea is that we will distribute the total power and in different or equal, in this case, all the module, each of the modules will have the same power that will be the total power divided by the number of modules. This seems sensible. And this worked very well in a new system. But what happened when after a few years, one of the module fails and needs replacement because there are faulty device or capacitor or whatever it is, then we replace by another that was on the shelf. We replace this is taken out. The company will repair and send us to the shelf waiting for it. So from now on, not all the device or not all the module have the same age. Some of them have limited the life, others are new, brand new, others no. So it's after some time, we will have differently aged cells. So we may have this cell, number 2, for instance, with that have been working for many years and the life expected lifetime is lower or shorter than the previous ones, that the others. But if we insist in using this, that is this, what we explain, same power sharing for all of them, then probably it's not the best option. What about redistributing the losses or the power between the modules? So each of them have a different power depending on the age, but the total, of course, is the total power is the same. Of course, we are not changing the total power. Let me show you this example. Imagine that the cell 1 has has been working for a long time, while the other 2 cells are brand new cells or younger cells. Then we can distribute the power equally. That is what we are doing in the time between this point at this point. Then all of them have, the 3 cells have the same power, okay? Consequently, they have the same temperature, but the lifetime is different. The lifetime of the cell, the old cell is considerably lower than the lifetime expected for the younger cells 2 and 3. So what will be the lifetime of the system? Oh, the lifetime of the system will be marked in dashed line. So it will be this one, the lifetime of cell 1. So we have to expect a failure in this time. But what happens if we apply, if we apply from this point the active power routing? Then what happens? That we decide to increase the power in the younger cells and decrease the power in the old cell. So the temperature consequently will drop here and be reduced here. Consequently, this temperature will make the lifetime of the cell, the old cell, to grow, and the lifetime to the younger cells to reduce. The consequence is that the important thing is that the lambda, the lifetime of the system, will be increased in this amount. Okay, so we have an increase. Let me explain you with another example. In this case, we are representing what is the normal operation, all cells with the same power, and this is applying the power routine. Of course, it depends on the industry, what the kind of industry we may consider acceptable. For instance, 1% of failure probability, or 10%, or any other value. If you consider an example like aeronautics with 1% of failure probability, then you can see that there is an increase of almost 2 years. Okay? If the increase or if the industry is working with 10%, but like renewable energies or something like that, the increase is about 1 year. The time till the next operation. So as you can see, working with this is very, very interesting. But it's for free. Unfortunately, it's not so easy and it has some drawback, but we know how to solve the problem. That is what I will explain with the example of the DC to AC converter and later with the DC to DC converter. Then we were mentioning the MMC. Everybody knows that MMC has a cell very simple with two IGBTs, or two switches and two diodes, and plus a capacitor connecting like this. Or the CHV. What we will explain now can be applied to both cases. I will work with the CHV converter because examples. First, if this is the conventional phase shifted PWM that we're using in the cascade H bridge, in this case with 3 cells, everybody should know this. And the idea is to have a phase displacement of 180 degrees divided by number of cells. So we will have, in this case with 3 cells, we will have 60 degrees, as you can see here. This is the first for cell number 1. The second is exactly the same, but displaced with a displacement of 60 degrees. And the second has 120 degrees or 60 with respect to the previous. With this modulation technique, we have, of course, the same reference that will give the same for all of them, provided that this voltage is the same for all the 3 cells. Then, assuming that we have 100 volts, then we will have in each of the output A1, A2, A3. We have these that are very similar, but not exactly the same. When we sum making this connection, we have the voltage between the output and the neutral point, and we will have not 3 levels like this, but we will have 7 levels, 1, 2, 3, 7 levels. Okay. Then, how are the harmonics? It's important. This waveform looks that we are using kind of a high frequency. There is a multiplicative effect in the frequency, and we will see in the harmonics. Well, all the formulas from now are taken from this book. It's a very good book that explains very clearly all these phenomenon and the harmonic, how to calculate. This formula gives us the harmonics that appear in a modulation like this. We can use this index K that depends on the group M1, 2, 3, and etc. And we can count from, in this case, from -2 till 3, so 6 harmonics in this group, and so on. So with this formula, we can calculate the amplitude of the harmonic. This A is this one. So I cannot explain too much the formula, but because there is no time, but you can check in this book, as I said. Again, we take the previous formulas, and if we want to make a particular harmonic equal to 0, then we have to solve to make this real and non-real part equal to 0. Okay. Then, if we consider the balanced operational condition, that is the same modulation index and the same voltage in the capacitor, in the input DC, then we have to solve these equations. They are simplified, and if we apply the previous formula that we say for the normal modulation, then we can see that effectively all the harmonics are 0 between m equal 1 to m minus 1, independently of the value of the number of cells. What happens? That if we do a simulation here, we can see that for 1 kilohertz carrier frequency, and in this case is 3 cells, then we see in one of the cells we have the harmonic center in 2 kilohertz and multiples. But in total, in the total in the output voltage, we see that all the harmonics below 6 kilohertz, the groups of centering 6 kilohertz disappear. Also, if we are in a three-phase, then all the three-plane harmonic will disappear, so it's even better. Okay, so this is very good, of course. But what happened? In this case, I will use same frequency, but with 4 cells instead of 3 cells. It doesn't matter. Then, till here, with this, in this time, we are applying in a balanced system. So the same modulation index is used. So we have this waveform, the blue waveform, that is with 9 levels, of course, and we see that the harmonics are the blue harmonics. There is nothing here in blue. But what happens if we apply the active thermal control, distributing the power routing? Then each of the waveform is different, so the sum of all of them will give us a harmonic like this. Then, unfortunately, we get all these harmonics, so we have to pay for a more complex filter. Let's say nothing is for free, okay, but can we mitigate or eliminate this effect? The answer is yes, of course. Let me see how we do. Imagine that we have 3 cells in series. One of the harmonic that isn't is like this will be displaced 120 to 140 degrees multiples. So we have 3 vectors for the harmonics that the summation will be this one, meaning that there is a harmonic in the output with this angle. This is what we got, of course. But what happens if we move this harmonic, not changing the amplitude, to this position and this to this position? You can see that this harmonic will disappear. The resultant will be 0. In other words, you can see when you are rotating or changing the angles, then you can eliminate one harmonic. So this is possible geometrically. So why not work on this? Okay, we can do in two approaches. We have done in two approaches. One is based on the fundamental frequency harmonic discretion, the previous formula for the harmonic, or another one that I will explain later, based in the sampling time harmonic discretion. Okay, so we saw this formula first, and if we want to eliminate, for instance, these two harmonics that are the largest one, then we can solve this equation, making it 0, and the solution will be something like this. So it's a geometrical and very simple problem, and we can do it in every cycle. How we do? Okay, the solution says that instead of 240, we should use 258 degrees for one of the phase 3, and for phase 2, we should use 126 with 3.3 instead of 120. Remember, I'm using one phase, not three phases in a three-phase system. It's the three cells that are in cascade, okay? Then using these angles, these two harmonic have disappeared. We have made 0. But still there are a lot of harmonics. So this is a first step that is improving, but not solving the problem. What to do? The other option is using calculating the harmonics in the waveform that we have. Then this is the Fourier formula, and we can make this harmonic equal to 0 if we are interested. So basically, we can eliminate one harmonic using this formula. Basically, we have finally these two angles that can be calculated in each instant, where the x are defined here, and so on. Then in an example, we can work in 3 cases. One case is using the same modulation index for the 3, and 0.95, for instance, and 150 volts in the DC for the 3 cells, same. Then applying the conventional balanced, that is in this condition, we find this. It's 3, so it's centered in 6 kilohertz. But if we change to different values, that is, we can use different modulation index per cell, assuming that each of them have different voltages, then we will have an unbalanced operation with pairing all these harmonics. If we use the variable angle that I explained before, using the formula in this previous slide, then we are adapting the angles like this, between 50 and 70 something degrees for one of them, and the other around 120. Okay, then we will practically eliminate all these harmonics, but still we don't know what to do here. Even with this method, we are making this worse than we have previously. So we have to be careful. Okay. It's a better, because it's a better step, but not totally perfect. So we should try to deal with several harmonic groups, and also extend this method to more than 3, because we are doing for 3. Solving analytically for more than 3, there is no evident solution, so you have to do numerical. Then we go back to these formulas, and instead of making the harmonic equal to 0, we will define a objective function like this, where we take into account the amplitude of the harmonic divided by k, the order of the harmonic, and this summation can give us a value that, depending on the angles, we will have a different value for this objective function. Our goal will be to make all this harmonic as lower as possible, but all of them at the same time. So this can be done with any mathematical search algorithm that will find the global minimum of a function like this. We are using the change market algorithm that is represented here, but of course, this is not the important part because you can do with any mathematical search. There is a taboo search or many methods that work well. But we found that this worked very well, and I'll show you the result. Let me show you 3 examples or three scenarios where we have 4 cells, 5 cells, and 6 cells, and randomly we selected several values of the DC voltage different, all of them different, and the modulation index chosen randomly also, using the carrier frequency of 1 kilohertz again, and output frequency 50 hertz. So this is the scheme of the CHP with the voltage in each cell in this case, and the control card that have been developed all in our lab. Then in the first scenario, that is with 4 cells, we are able practically to eliminate all the harmonics in this part. The blue harmonic are now in this case, and some reduction in this part. In the second, with 5, we practically reduce all of them, and with 6, we reduce all of them. How fast is it? Practically in 100 milliseconds, you have the 100 microseconds, you get the angle in a steady state. So what happened? That we can say that we reduce the filter, less volume, weight, and cost, but there is no extra cost. We are not adding any hardware, just software. Okay. Okay. So we saw the application to DC to AC. Let's apply now to DC converters. The 2 examples I mentioned before are a multi-string PV system where we have different, in this case, I wrote 3, but maybe more, converter, DC to DC converter, normally boost converter, that are feeding the inverter that connect the system to the grid, but as a filter, we are using this capacitor. Here is the same. We have the same capacitor, and in this case, 3 cells boost converter for a wind turbine that has a converter distributed like this. It's an example, of course. We can find many other examples. Okay. In any case, for both cases, we have a thermal control measuring the temperature in each of the modules of this one. So we can try to make to control in a slow dynamic controller. We can distribute the fraction of the total power for each of the modules, and in each of the modules we will control a normal control to keep this voltage constant or the current or any other interesting control. Applying this, we may do exactly the same. That is, the young cells will increase the temperature of the power, and the young cell will decrease the power. Okay. Consequently, the temperature will increase here and decrease like this. So the in the temperature, the junction will be similarly changed. In this case, it reduces 4 degrees and increases 2 degrees in the young cells, and same for the diode. So basically, what we will have is a extension in the lifetime of this device and shortening the life of this, as we explained before. So we may show this sample with 3 cells where the power is different. This is the power losses are different, so the temperature will be different. And maybe we can see here how they evolve with time in months, where without the active thermal control in dashed, and with the active thermal control, you see how they are converging. So maybe here we can see how originally this part was the system, because it's the worst case, and the timing is increased by 24 months because we are moving this in this position to this position. Okay, so it has any drawback? Well, let's see. This is one example in the PV. This is a very typical where we are displacing 120 degrees between one and the next, and one of the next and the next waveform. And this is the output that is feeding the inverter and the capacitor. And then the harmonics in this case will be 12 kilohertz, because we are using a carrier frequency of 4 kilohertz, and we have 3 of them. Okay. But what happens if we don't have the same waveform in each? That is, we have different values. Then the waveform is like this, not so nice as this one. But this means that there is a new harmonic that was not present in the balanced one. So should I be concerned? In the previous, in the DC to AC converter, we were worried on the harmonic because we have to filter to be connected in the grid, because the electrical companies, the electrical utilities fix maximum for the harmonics, the grid code. But now it's just in my capacitor internal, so maybe I can ignore it or not. Let me see the effect. We showed this before, and we need to know what is this power. So if there is different harmonics here, and there is ESR resistance, then the power will grow. If this grows, the temperature will grow, and in this formula, we will have something that will affect greatly to the lifetime. So we have to be careful. Take care of this. Then if we analyze the harmonic in a typical waveform in a boost converter, then we have this. You can find in any book or calculate by yourself, no problem. Then we can make a similar thing that we did before. But in this case, we are considering the case of the ESR is constant. Maybe, if not, we will put this summatory with multiply by the resistance at this frequency. It's no problem. It's just a few more calculations. Okay. Then applying the same algorithm that previously the exchange market algorithm for the this objective function, then we can apply this to several cases. I have shown here 4 cases, but not all of them are drawn here. But for instance, the case 1 is a balanced condition. Second is using the conventional angles in the now unbalanced. In this case, we are eliminating only one group of harmonics. In this case, we are eliminating three group of harmonics. Then for this case, we have are eliminating one group of harmonic. We have two possible solutions corresponding to 240, 150, or 133, 212 the angles. And the solution is perfect because there is no harmonic at all. The rho, the objective function is zero. If we are trying to eliminate three harmonics, then we don't have exactly zero, but we reduce, and using these two angles, we find a local minimum, global minimum that will give us a better lifetime for the capacitor. But let me show you some example with two different inductances, this inductance 3.6 or 1.8. We will consider two different capacitors with 2 and 5 Kelvin in degrees per watt of thermal resistance. In this case, 2 is the unbalanced that I will take as 100%. We will see that the temperature is 31 degrees or 38, depending on the degrees of the thermal impedance. In case 3, with eliminating one group of harmonics, we get 27 less, so 4 degrees less, and 8 degrees less with this. If we use the second one, the small inductance, then is practically there is bigger difference even. But this is important, but we can show the next case that this. And how is the extension of lifetime is 33% or 100 or 77 more. The new lifetime is 77% longer than previously. So this is very important because we have extended lifetime and it's for free. No, we don't need to do anything about this. As conclusions, we have been using the active thermal control via power routing. We show that it's an effective method to manage the power devices and capacitor remaining useful lifetime. It has been applied to modular inverters and DC-DC converter that is very well suited for fault-tolerant operation and reduce maintenance costs. But of course, it has some drawbacks in creating low-frequency distortion. But unfortunately, with techniques of controlling the angles of the modulation method, we mitigate this drawback for free. So we can reduce the cost of the output filter in modular DC to AC system, extending the lifetime of our capacitor in interleaving DC-DC converters system. Finally, I want to show you some references that some people in the group have been working on it, where you can find the details that I have been showing, and more things that we have no time. For instance, how we can modify the using the power routing to extend the lifetime. This is a very recent that got the magazine Best Paper Award, where you can see this curve that I used previously, and how we can reduce using the ATC, the power routing, the number of maintenance that normally could be like in blue and the red one. So you can find much more details. In this case, we show how we can change the variable angles and how we can reduce the harmonic here using the different angles with much more details. Also, how we can clamp, I didn't explain this in the presentation, how we can clamp during part of the time to reduce the losses and how this affects to the harmonics, but finally it can be compensated. Also, this is the application of the variable angle on a large number of power cells. And this is for the DC to DC. We have two papers in recent two papers on this, explaining how we can equalize the power or the temperature in different modules. Finally, as I'm also editor-in-chief of the journal, as it is a new journal, I want to remind you that it's open. Journal is open to receive your papers, and of course, it's an open journal, meaning that it's open, that there is no paywall for accessing the papers. So probably meaning that you don't need to pay for it if you want to read the papers as a reader. You have to pay for it because there is an article processing cost as author, but we apply many discount to IES member, also for conference in IES. If you come from a technical committee that endorse your paper, you don't have to pay anything. We have a group of discount that is in the web. The main characteristic is the rapid turnaround. We are in between 4.5 weeks now from submission to final decision. We use almost just no decision, but there is also possibility to have a minor, single blind per review, and no page limit. Only for technical reason we can limit the page. It's online, there is no printed, and it's all open access. Basically, if you are interested, you can contact me and I can give you more detail. But now the data that I have is that next year in 2022, we will have impact factor, that meaning that all the papers that will be submitted from now on will be published in 2022, and we will have an impact factor published in 2023, of course. And that's all from my side.